Hello everyone, welcome to this tutorial on the sketches of infinite data and algorithms for real-time data insights. My name is Vishnu Pendyala. Uh, I am with San Jose State University in the Applied Data Science Department in the new College of Information, Data and Society. So today it's going to be a long talk. It's a tutorial on infinite data. So infinite data refers to real-time, unbounded data flows. So where do you find such flows? Such infinite data is quite common in Internet of Things, social media, finance, web analytics, and many more areas. But we have infinite data flowing, but we don't have infinite memory to store them. That means we cannot store the entire stream of data. On the other hand, we need real-time processing. That is the velocity V of the four V's of big data. We need low latency algorithms. We need to process data on the fly. And there is also a concept drift. Data patterns evolve over time. So we will have to employ approximate statistics with compact data structures. So we are in for some serious business today. So hopefully you'll all be attentive and you'll like the tutorial because a lot of uh, current days applications are driven by these algorithms. Oh, it got muted. Sorry about that. Thanks for reminding me. Uh, so yeah, what I was saying is we take for granted many amazing things that happen around us. Website traffic for social media sites like Twitter, which is now called X, is infinite, right? So, so how are trending hashtags from the near infinite microblog posts, unique visitors, and other distinct counts in the near infinite website traffic determined? Did you ever wonder about? So you'd have seen these kind of trending hashtags and you would have seen unique visitors and several other analytics that are shown on the microblog sites. So this snippet, this screenshot is from Twitter, which is now called X. So you can see the trending hashtag. So how are they determined? It's not it's not exactly intuitive to start with because there are some unique requirements for generating these hashtags. Uh, so the algorithm that we come up with for determining these hashtags, for instance, needs to avoid fads, random spikes, and things like that. We want these hashtags to be very trending. In fact, one of my favorite news sources is these Twitter hashtags. I don't even look at Mac News. If something really important is going on in the country or in the world, for that matter, I don't look at the news. I go to Twitter to see what is trending because these are really hot. By the time the news channels air the topic, by the time they collect the information formally and vetting goes on, it'll take time. But on Twitter, the news is almost immediate. So that's the reason why I typically tend to pay a lot of attention to these trending topics, which provide really unique insights. And the other thing, good thing about these microblog posts is that they express opinions, very frank opinions, right? They are not vetted, they are not politically correct. So a lot of course, some of it may not be really to our appeal, but that's okay. I mean, we can still get opinions, frank opinions. So the other interesting thing that's happening around us is, of course, um, the large language models, generative AI. That's taking a whole lot of wonder um, among many people, right? So how do machine learning algorithms, how are they able to answer questions from any nook and corner of the World Wide Web? So we all know that these days, when we search the web, for instance, I put the same question into Google search here, and Google AI overview gave me some answer. So, so this information is generated based on the content on the World Wide Web. So how was it able to answer this question in such short notice? A World Wide Web is almost like infinite to us, right? I mean, for us people, it's almost impossible to read the whole World Wide Web. It's almost infinite. And the questions need to be answered immediately without a lag. So how is machine learning powering these kind of applications? And the next scenario is blogging sites. I'm pretty sure a lot of you are enthusiasts here uh, who would be probably writing a lot of blog posts. So how do blogging websites avoid recommending articles a user has previously read? So if you look at Medium, for instance, Medium recommended, when I visited Medium, it recommended this article to me. So what is the infinite data here? It is a continuous stream of reads by the users. It's a stream of events, and the event is a user reading a blog. Most of the algorithms we studied today are ideal when memory is constrained. And the other important thing is perfect accuracy isn't required, like in this case. We are not interested in 100% accurate count of or accurate recommendation of a article, of a blog. We're okay even if it is off by a little bit. So, so this is an important design consideration for large-scale big data systems. Accuracy can be compromised to some extent. So that's the design consideration we have to keep in mind for big data systems. Another example of velocity aspect of the big data that fascinated me is the process that happens when we upload a YouTube video. So last year or a couple of years back, I went on a cruise, and there was karaoke, so I sang some songs there. My kids recorded it, and I uploaded the songs to the recordings to YouTube. And within seconds, YouTube flagged that there is a content ID claim on your video, it doesn't affect my channel. This is not a copyright strike. So it immediately found out that the song I was singing was copyrighted. Fortunately, the owner of the copyright allowed others to also record the same song. But only thing is they get portion of the revenue if I earn anything, that is. Uh, so the interesting thing to note here is, in spite of my own voice, it could check the music, rhythm, tune, and other aspects of my song and quickly identify that within seconds or maybe microseconds. It could identify that there is a copyright claim on the song. So how was it able to check nearly a billion, maybe even more, I'm not very sure, but billions of videos in matter of microseconds or seconds? So we don't know the algorithm, but the algorithms that we are going to cover today will give you some insights into how these things can be done. So in general, how can we answer complex queries about enormous data streams without storing them entirely in real time? The answers must be in real time. So the answer often lies in clever approximation algorithms and data sketches. So these sketches capture essential properties using vastly reduced space. So the infinite flow of or relentless flow of data in modern systems presents significant challenges. These data streams are often too large to store and too fast to process exhaustively with traditional methods. So this talk will introduce some key sketching and approximation techniques. These techniques help generate real-time data insights by processing data streams. So when we talk about infinite data, we are talking about a stream of events. So um, it's not Netflix or YouTube streaming videos. It's a stream of events, right? The input rate is controlled externally. So in case of Netflix and YouTube, the stream is controlled by the providers. But in this case, the input rate is controlled externally. We can never predict the peaks of this streaming. Uh, so we already talked about some applications like this, but there are many, many more. For instance, this page shows the real-time public feed of activity on GitHub, right? Let me click on this GitHub. And what do you see here? I hope everyone is able to see the screen, uh, the GitHub files, the events happening on GitHub. So as you can see, this page is showing the real-time public feed of activity on GitHub. So in fact, you can look at the code also. You just see that somebody pushed, okay, let me start here. Somebody raised a pull request, somebody created a branch, somebody created somebody pushed a commit, so on and so forth. So this, as you can see, it's almost like a fire hose. It's rapid fire, right? So this is what we are referring to as infinite data. So this is almost infinite. There's no end, there's no beginning. It keeps on and on and on and on forever. So that's why it's called infinite data, right? So, so that is the idea, right? I hope you got an idea of what infinite data is. So in terms of software writing software for this kind of infinite data, we treat infinite data as a rapid stream of tuples. So what is a tuple? if you have studied set theory in high school, if you remember set theory in high school, a tuple is an element of a Cartesian product. I mean, all that math is not really required now, but anyway, it is basically you can think of it as a set of items, right? So for instance, uh, I tried to guess that the stream of tuples for the GitHub application we saw just now, right? It could be having type, it could be having repo, actor, created at, payload, and so on and so forth, right? So this is the kind of in data that we want to process. So typically we represent it as we get it as in the JSON format. So if you look at the tuple in a little more detail, the type is it could be a push event, it could be a pull request, it could be a create branch, a repo name, and a lot more details. But still, this can be treated as a tuple. The important thing to note is that the rate of arrival of stream elements is not under the control of the system. And the other important thing to note also is that it is not possible to answer queries from the archival store. So archival store can be examined only under special circumstances using a time-consuming retrieval process. So we need to process everything in real time in single pass. We cannot go back. So the working store might be the main memory itself, not even the disk. Sometimes it could be the disk, but quite often it's the main memory. So that is the idea. So what are some of the problems and peculiarities when dealing with streaming data? Uh, I know this is a webinar mode, so I don't know how many of you can unmute yourself. But anyway, feel free to post your answers or comments on chat window and questions in the Q&A panel. Um, so in the interest of time, I'll probably answer it myself. So streaming data is like a stream of water, no beginning, no end. It's massive, continuous, um, and there could be spikes unpredictably. So it requires robust scaling and horizontal scaling solutions. The other thing is the processing should be real time or near real time. And it has to be single pass. You cannot go back and check information. You cannot go back for a second pass. So data is continuously flowing. Once the data is passed, it is gone from your hand. That's it. I mean, you could store some important information in the archives, but that is for rare uses, not for regular use. So that means we need optimized pipelines to minimize delays. We need to avoid, the algorithms must avoid bottlenecks, and the memory management must be tuned for efficiency. So streams are theoretically infinite. So memory and storage management must be designed for ongoing data flows without a fixed endpoint. And the other problem with streaming data is that the data is non-homogeneous. It's not uniform. So uh, because we want real-time processing, even algorithms with linear time complexity are unacceptable, let alone quadratic complexity or higher. So the complexity is typically constant or needs to be logarithmic, right? So we need really very efficient algorithms, and that is the purpose of today's tutorial. So let us start with a very simple algorithm. So you would have seen this kind of scenario, this kind of screen when you do a Google search. right? In order to show you the most relevant results, we have omitted some entries very similar to the 47 already displayed, right? Um, so, 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 so obviously the large number of hits for the search that I did. So therefore, Google doesn't want to show all of them. In fact, not just Google search, many similar applications do the same thing. I cannot recollect immediately, but I have seen other applications do the same thing. So we need to sample data effectively. So what is happening here? So Google's algorithm basically sampled the infinite data or whatever the results that it obtained, and it only showed a sample of those results, right? So sampling is key here. Uh, so so how may Google have selected the results displayed among the very similar stream of hits? So one way is the first K hits. Then if it chooses just the first K hits, the sample may be biased, right? Of course, it has a PageRank algorithm, and it uses several thousands of hundreds or thousands of algorithms to rank the pages. But still, the sample would be biased. It will not be a representative sample, right? So the sample is biased. So does it randomly choose the K pages to display? May still be unfair, right? Randomness may not be a true sample, right? So we need it could be something else. We don't know for sure what Google is using because it's all proprietary, but we can guess. So that leads us to the first algorithm for fixed size stream sampling. Um, but why is even a seemingly simple task like sampling difficult for streams? So first reason is that the memory is limited. The data stream is infinite and rapid, but the memory that we have at our disposal is limited, fixed, and constrained to store the sample. And the other thing is uh, the one-pass nature. Once a data item is processed, we cannot revisit it. We cannot go back, right? Once it passes, that's it. So it's a one-pass algorithm. And the length of the stream is unknown. And the other thing is the data is not guaranteed to be identically distributed. So in the case of Google search as well, not all results are important or interesting, right? Um, and then, yeah, like I mentioned, no time for a second look at the stream. So that brings us to the algorithm called reservoir sampling. So reservoir, we all know, has limited capacity. So just like reservoir of water, we want to build a reservoir of data using a sample. So once again, the data is non-stationary. That means the distribution changes over time. So any ideas on how we want to do this? So you can think, um, but it basically the algorithm constructs a random sample from a data stream without knowing its length in advance. But the random sample cannot be like completely random. Like you cannot do whatever you feel like, right? It needs to follow certain properties. And then we are interested, in this case, we are interested in a fixed size reservoir of samples as the stream is processed. And the sampling is with replacement, right? That means if you have taken an item into a sample, then the assumption is that the the item can repeat, right? Um, and then the algorithm ensures that each data point has an equal probability. So this is the property that the randomness should obey. It is called statistical invariant. So the property that the random sample should follow is that each data point should have the same probability of being included in the sample. We should not bias any single or multiple data items. Every data item should have the equal probability of getting selected. So this is the trick. Why is this the problem? Because the data is continuously moving, right? It is not stationary. If it is stationary, then this can be easily done. But the data is continuously moving. So that is what makes it a challenge. So it uses a fixed amount of memory. That's why it's called a reservoir. And that's why it's suitable for streaming and limited memory environments. And the data, of course, needs to be processed in single pass without the need to store all data points. We cannot go back. Um, so the main challenge is the statistical invariant property, right? Um, suppose the fixed size of sample we want is k, and we have seen n tuples or elements so far. So I'll use elements, tuples interchangeably. Um, the statistical invariant, once again, is that each element in the sample must have the same probability, and that probability should change with each incoming element. So that is the interesting part. The probability is not static, it is dynamic. It keeps on changing with incoming elements. So probability of any data item being in the sample from the n items seen so far in the stream is k by n, right? If you are choosing k items from a data with n items, if each element has the same probability, then it should be k by n. But the challenge is that the number of items is not constant. When a new tuple arrives, when a new n plus 1 item arrives, the probability changes to k by n plus 1. So our algorithm should make sure that this is preserved. So the probability should automatically change to k by n plus 1. So that is the challenge. So how can we ensure the statistical invariance property? The solution is reservoir sampling. So what is a reservoir sampling? So this is a pseudocode for the algorithm, but essentially we store, so the input is a stream, a sequence of elements arriving one by one. So this is nothing surprising. It's a data stream of events or something that represents an event. And we want a sample size of k. Um, so the output is a reservoir sample of size k. So the first step is to store all the first k elements of the stream to this to the reservoir, right? So initialize an array which represent the reservoir S to store the first. Sorry, it should be k. I think I'm sorry. It should be k. First k elements of the stream. Then for each element in the stream, uh, for n is greater than k, that means we have already stored the first k elements in the reservoir. Now the k plus 1th element comes and so on. So for each element beyond k, this is what we do. With probability k by n, we pick a random index in the reservoir to replace, right? So we have the reservoir with us, which is this array S with k elements. Now when a new element comes, we want to kick one element off of this array with a probability of k by n, right? So we will not always replace the element. We will replace it with a probability of k by n, right? Uh, so how do we do this? We set a random integer between 1 and, sorry, I should have written k here. It should be k actually. So we pick a random integer between 1 and k, and um, uh, we replace the random integer with this, with the new element in the string. And then we return s. That means k by n times we do this. And the remaining n minus k by n times, we don't do this. We don't do anything, right? Only k by n times we replace the element. Remaining times the sample remains the same, right? So that is the idea. So I hope that is clear, right? It's a simple algorithm. Um, so, so this is intuitively correct, right? Our intuition tells that this preserves the probability k by n when there are n elements, and if there is n plus 1, the probability automatically changes to k by n plus 1. So intuitively it is correct, but how are we going to prove it? So algorithms need to be proved, right? Just intuition does not um, uh, prove the algorithm, right? So for that, we need to see the possibilities and evaluate the probabilities. So how many possibilities are there? What are the events? And what is the probability of each combination or single event happening? So that's what we need to look at to prove that our intuition is correct, right? So a few things can happen with respect to the element I in the sample, right? So we are now proving that our intuition is right. Uh, okay, so if element n plus 1 is discarded, so that means there's no change in sample, right? So that is the first event that can happen. A new element n plus 1 has come, and we simply decide not to put it in the sample. So we discard it. So then we don't have to do anything. That's the easiest case. Now, when the element n plus 1 is not discarded, that's when the process starts. So we have to kick out one existing element in the sample. So one existing element in the sample needs to be replaced. And there is a chance that this particular element I in the sample may be replaced, or it may not be replaced also. So we randomly choose one element and we want to determine whether it follows the statistical invariant property of remaining in the sample, which is k by n plus 1, right? That is our goal. So we randomly choose an element I. So if it is true for element I, then it will be true for all the elements in the sample, because we did not make any assumptions about this particular element I. So let us consider just one element I and see its probability. So one thing should not change, which is a statistical invariant. The probability of the element I remaining in the sample should be same as others, which is k by n plus 1. So then we need to prove that the probability of element I is in the sample at n plus 1th occurrence is k by n plus 1, given that the same probability before n plus 1th element arrival is k by n. So the probability simply changes from k by n to k by n plus 1 when a new element arrives. That is what we need to prove. So if we prove this, then our algorithm is correct, right? Agree? So now let us look at the dynamics, sampling dynamics, right? We need to prove that the probability of element I in the sample at n plus 1th occurrence is k by n plus 1. How can we find that? It is a I in the yeah, so it is a joint probability. Two things must happen, right? What are the two things that must happen? Element I in the sample is kept in the at the nth occurrence. That means it should have been there in the nth occurrence of the data stream. And element I in the sample is kept at the n plus 1th occurrence also, right? So, so element I is not picked up for replacement with the new element in the stream. So that is what we are trying to compute. So we are given that probability of element I in the sample is kept at the nth occurrence is k by n. We are already given this, right? The very fact that it is in the sample, we can assume that it is k by n. And if it is k by n, then we are proving that with n plus 1th element, it will be k by n plus 1. And by mathematical induction, it holds for everything, for every element in the stream, right? You all know mathematical induction. And the base condition is trivially satisfied, right? What is the base condition? We choose the k element from the sample and k elements from the stream initially, and the probability will be 1. The denominator n is equal to k, so k by k is 1. So it is trivially satisfied. Then for n greater than k, these probabilities all apply, right? So we need to figure out the probability of element I in the sample is kept at the n plus 1st occurrence, 1th occurrence, right? So any guesses on what all these probabilities are, like the individual probabilities? So we'll see it in a little more detail. So we'll look at the relationships between the probabilities first. At the occurrence of the n plus 1st or n plus 1th tuple in the stream, the probability of element I is kept in the sample is a combination of two disjoint events. What are the two disjoint events? If the element I is kept in the sample, what two things should happen? So there are two things that, no, sorry, one of the two things should happen, not both the things, but one of the two things should happen. What are the two things? Element n plus 1 is not discarded. So the two events that could happen are n plus 1th element is not discarded and element n plus 1 is not discarded and element I is not picked. So these are the two situations when the element stays in the sample, right? So either the new element must be discarded or the element should not be discarded and element I is not picked, right? Those are the two events, disjoint events. If this happens, this does not happen. And if this happens, this does not happen. They are disjoint because in the first case, we discard the new element. In the second case, we don't discard the new element. And there is a chance that this element I is not picked. So now let us compute this second. The first probability is relatively easy, but the second probability is what we want to focus on. So what is the second probability? So when will this happen? Element n plus 1 not discarded and element I is not picked. The, the very wording tells you that two things should happen together at once, right? In the first case, these events were disjoint, but in this case, these are joint events. That means both must happen, right? So it's an AND. So when it is AND, we multiply. When it is OR, we add. Disjoint events, we add. Joint events, we multiply. So element n plus 1 not discarded. That's the first situation, first event that must happen. And element I is not picked. So now we have to compute individual probabilities for this, this, and this, right? These are quite atomic. We should be able to compute the probabilities easily. So, so what are the probabilities? So the probability that the element I in the sample is not picked, if it is picked, the probability is 1 by k. If you remember the pseudocode, where was the pseudocode? So we are picking a random index in the reservoir to replace. So random index is between 1 and k, right? So the probability of getting this particular I in for R is 1 by k, right? Because we are choosing a random integer between 1 and k. So, so the element I will be picked up with a probability of 1 by k. That means it will be picked to replace. That means it will get kicked out with a probability of 1 by k. If it is not picked, then it will be 1 minus 1 by k. Easy one. And element n plus 1 is not discarded. Is, remember again back to the algorithm, we don't discard the element only k by n times, where n is the timestamp, right? Nth tuple is coming. Then with probability of k by n, we don't discard the new element. So that's why the probability of the new element not getting discarded is k by n plus 1. In the pseudocode, it was n, but now we are considering the n plus 1th item or tuple. So that's why the denominator is n plus 1. With probability k by n plus 1, we do not discard the new element. And so the element n plus probability of the element n plus 1 discarded is 1 minus k by n plus 1, right? It's negation basically. So the probability that the element I in the sample is not replaced. Any guesses what the probability is? So it is a complex expression, right? So remember this complex expression. It's a joint it's an addition of two probabilities of two disjoint events, and one of them is again a joint event. So it's this complex this thing. So we substitute the probabilities for each one of these three probabilities in the expression. So for the first probability for the disjoint event is 1 minus k by n plus 1, which is that the element n plus 1 is discarded. And when the n plus 1 item is not discarded, it's a joint probability of k by n plus 1 times 1 minus 1 by k. So if you substitute and simplify, you get n by n plus 1. So the probability that element I in the sample is not replaced is n by n plus 1. Now, if the element I is in the sample at the n plus 1th occurrence, it implies that it was already there in the sample at nth occurrence as well. And the probability that it was there in the sample is k by n. So if an element is in the sample at n plus 1th, two things should happen. One, it should be in the sample at timestamp n, and it should be in the sample at timestamp n plus 1. So the first probability is k by n. Second probability we just derived n by n plus 1. So when you multiply both, you get k by n plus 1. So our algorithm is correct. So that is the algorithm. So in big data, algorithms are quite easy to comprehend. It is the proofs that are a little bit challenging. So you need to spend some time thinking about these proofs. I will upload the slides on the internet. So if you are not very, um, if you are not quick in grasping the whole thing, you can just spend some time on the slides. You will understand for yourself. And of course, I'll fix the typos. So there are many applications of reservoir sampling, bioinformatics, sampling. Bioinformatics is a huge big data application, right? Um, Google's AlphaFold won, the researchers of AlphaFold won a Nobel Prize. So that is the impact of bioinformatics. And in machine learning, we need to sample as well, scientific simulations, memory constrained devices, real-time analytics. So the simple stuff on the slides, I will go over very quickly because I have like 103 slides. So these are easy stuff, so you can easily read them or understand them when I post the slides online. Uh, and then web crawling, we already saw an example of Google. So that is we don't know if Google is using reservoir sample exactly, but at least reservoir sampling is a potential candidate for those kind of applications. Um, In fact, the stochastic gradient descent algorithm itself is a good example for streaming. It's a streaming algorithm. You sample the data. Of course, it's not an example for reservoir sampling as such, but it's a very good example for streaming algorithms. So that is the first algorithm. Hope you got a feel for what is involved here because of the infinite flowing data. Now, the second algorithm or the second application we want to cover is filtering, right? Filtering has many applications, right? In your databases, you have deduplication, right? You want to find unique elements. And spam filtering is another example. You want filter out spam emails. So many applications. But now starts the fun part. Why do I call it fun? Because would you design a data structure that sometimes tells you lies? That's what we are going to do now. We are going to design data structures that sometimes tell lies. Of course, you already must be using ChatGPT and other generative AI tools which hallucinate, but I'm not talking about those things. That is also an example of big data algorithm which tells lies, which I will also cover shortly. So in the world of big data, we have to live with lies. There's no other alternative. So like Mark Twain said, right? There are three kinds of lies: lies, damned lies, and statistics. So this quotation comes to life now with our algorithms. So the problem is we are given a set of known tuples. We want to filter out unknown ones from a flowing stream of tuples. How can we do it? Any ideas? So one simple algorithm or simple intuition is um, to have a table or a hash or a dictionary, things like that. Um, so that is a popular way of filtering in the regular software world. So, so the known tuples can be email addresses in case of spam filter. So, so we basically store the safe tuples in a hash table, and as the data stream is flowing in, we check each tuple in the with the table with the contents of the table and check if it is safe and pass if it is safe. Otherwise, discard. Right? What is the problem with this? So if you design an algorithm using your traditional techniques, this is what you're going to do. But what is the problem? It will not work if there is no space for storing all safe tuples, right? And indeed, there is no space for storing all safe tuples, right? Even if I take, for instance, your spam email addresses, the genuine email addresses run into billions, right? So it's hard. So we need a new data structure, and that data structure is a sketch. So what is a sketch? A sketch is a representation, a small representation of the data. So a common theme with these data structures is that these data structures can lie. They will tell lies. So something new for big data is accuracy. So far in your algorithm analysis courses, you only studied about time storage trade-off. So the complexity was measured against time and space. But now a new trade-off has started, and that is accuracy. So you trade off accuracy for time and storage. So deterministic data structures always return the exact and correct result. So the examples are arrays, linked list, trees, stack, whatever you have studied in the computer science course are your deterministic data structures. What you study in big data are probabilistic data structures. So these can return an approximate or potentially inaccurate results, unlike the deterministic data structures. And typically, time complexity can vary depending on the data and chance. And linear complexity or more is just not acceptable. Linear complexity is just ruled out in most cases, right? Whereas in case of deterministic data structures, linear complexity is good. If you are able to get logarithmic complexity, it is very good. But linear complexity is typically good. When you go to these interviews, Google, Facebook, all these FANG companies, now it is called MANG, I believe, because Facebook became Meta. Um, so these companies test you a lot on data structures and algorithms, right? And complexity plays a big role in these interviews. So linear is somewhat acceptable, but they look for algorithms with logarithmic scale. But here for probabilistic data structures, even sometimes even logarithmic scale is not acceptable. You need to go sublog or constant. Um, and then the memory usage is also a constraint. We need to design algorithms which are very memory efficient. Um, Again, in the logarithmic scale. So the examples are Bloom filter, which we are going to cover now, and hyperlog, which we will cover in the next. That's the next algorithm we'll cover. So MinHash, I don't think I have time to cover in this session, but it will give you a good idea of what these algorithms are for. Um, so the use case is, the use cases for deterministic data structures, but for probabilistic data structures, it's big data, right? That's the use case where speed or space efficiency is a priority, right? So, so there's a major philosophical shift in modern computing, right? So the philosophical shift is that approximate answers are often good enough, right? And the other shift is in the efficiency, the demand for efficiency. For instance, as the name tells you, hyperlog uses memory proportional to logarithm of the size of the data. Log of n, where n is the number of unique elements. So that is the efficiency this algorithm achieves, right? So this means that the memory required to count 100 or 1 billion unique visitors is nearly the same, about 2 kilobytes. because that's the logarithm of a billion, right? It's about 2000 or something like that. So that is a drastic shift in the software data structures and algorithms that we traditionally learned, right? So this is an exciting world. But to understand this exciting world, we first need to understand another common theme. The theme is the data sketch. So big data is all about summarizing huge amounts of data using sketches. So we kind of sketch with a sketch pen of a real so we sketch a image of a real person, right? So just like that, a data sketch sketches the image or a representation of the real data, right? You can think of it like that. Um, and this is known by many names. It's typically not called sketch. In your generative AI, large language models, it's called model, right? Um, so model is basically a sketch. In machine learning, model is essentially a sketch. I'll tell you why it is a sketch. Okay, to understand this concept of data sketch, let us look at uh, a simple problem, right? So a stream of 9 unsorted natural numbers is read out to you one after the other. So there's a party going on, and just to um, pass the time and engage the people, there's somebody reading out 9 unsorted reading out a lot of puzzles basically to amuse the audience. And one of the puzzles is a stream of 9 unsorted natural numbers is read out to you one after the other. All the numbers are unique and less than or equal to 10. So only from 1 to 9. So these numbers you can see on the slide. Now, how can you tell which number between 1 and 10 is missing in the stream based on the following conditions? What are the conditions? You have space to store just one number, and numbers will be read out to you only once. You cannot ask the MC, the master of ceremonies, to repeat. It's a single pass processing. So any guesses? So I'll post this video. So if you are watching this video in the future, then please pause the video and answer the question to yourself. But in the interest of time, I am going to give the answer. The solution is store the sum of numbers read out so far, right? We know that the sum of the first 10 numbers is 55, right? N into n plus 1 by 2 or whatever, right? 10 into 11 is 110. Yeah. So n into n plus 1 by 2 is the sum of n natural numbers. So when n is equal to 10, it is 55. Subtract the sum accumulated from 55 to know the missing number. So you are storing just one single number, which is the sum of numbers read out so far. Subtract it, and the number that is stored is this. So you get the missing number, and the number that is stored is the sketch of the actual data. So 9 numbers were read out. You're not storing all the 9 numbers, you're storing just one number, and that one number is representative of all the 9 numbers, and which is the sum. So that is the sketch. That is the idea of sketch. We want to store just enough information about the data to be able to answer questions that we need to answer. So that is the idea of a sketch, right? So in this case, it is the sum of the numbers read out so far. It is representative of the real data, just enough to answer required questions. So this is a common theme across streaming algorithms. So in machine learning, like I said, in ChatGPT and everywhere, the model serves as a sketch. Why is it? So models are essentially machine learning models, I mean, or compressed learning. Model is basically something representative, right? So that's why it's called model. So this machine learning model is basically a representation of the data on which it is trained. Um, so let me check if there are any questions. 1 second. Okay, looks like there are no questions. Okay, so so model is basically, so in software, intelligence is essentially compression. When you can compress the data, that is called intelligence. That's it, right? So in the traditional machine learning, what happens is you have training data typically in the form of a table of data. So from that, you pass the data through an algorithm like logistic regression or support vector machines or some other such algorithm. Um, and you generate a few weights. So these weights are called parameters, right? Uh, and in case of human learning, something very similar happens. So the data on which we trained our experiences, education, you're attending this tutorial today. So you have, you're collecting a lot of experiences, getting enriched, you're getting education, hopefully. So all this is your training data. And our brain applies an algorithm uh, to generate a 10 to 30 trillion parameter model in our mind, right, of all the data on which we are trained. Similarly, in large language models like ChatGPT, they are trained on World Wide Web and who knows what else. No one knows accurately what all they train on. But suppose it's just World Wide Web. So it gets trained on a huge data set. And the very first version of which went public, I mean, the ChatGPT was having 175 billion parameters, right? Right now, the latest models, people say that they could run into several trillions. We don't know for sure, but it was 175 billion initially. Uh, so the process of creating intelligence is essentially compression. So we compress the data on which the models are trained into parameters. So ChatGPT model is essentially like a zip file. You all know, you must have used zip files, I'm pretty sure. Um, so it is almost like a zip file of the World Wide Web and whatever data on which it is trained. But the difference is that zip files are not lossy compression, unlossy compression. That means you can extract the original file. But with large language models, it is a lossy compression. You can never extract the original World Wide Web entirely. Because of overfitting, it can output copyrighted material, but to a great extent, you cannot extract the original information. So the program which does the inferencing for you, the ChatGPT program, is basically a few lines of C language, maybe 300, 400 lines of C language program. It's like the unzip program, uh, which answers the questions. That's it. So that is, so how about this puzzle that we had? Is this lossy compression or unlossy compression? So can we retrieve all the 9 numbers from the sketch that we had? It's a lossy compression, right? We did not store all the 9 numbers. We cannot retrieve all the 9 numbers. We can only retrieve this sum. So same thing with the machine learning models. We cannot retrieve the original data. We can only use the sketch to answer questions. So I'll give you more insight into this model, machine learning models. So suppose there is only there are two features, x1 and x2, and these features are for the same data. So maybe, I mean, I don't want to take examples. So assume x1 and x2 are features of the same data. Okay, let me take an example anyway. Say flowers, petal length and sepal length. These are the two features. So this is a very fundamental concept in machine learning. I just wanted to illustrate the concept of sketch through this in machine learning, I mean. Um, so, um, so which feature is more important to y in this model? Y is the y-axis and x is the feature. So which feature is more important? So in the interest of time, I'll give the answer. Uh, it is obviously x1, right? Why? So I'll give you an analogy. If your office experiences make you change faster than your home experiences, what does it mean? It means office is more important, right? It may it may upset your family members, but that could sometimes be the fact, right? You change more rapidly with the happenings in the office than you change with your home experiences. So in the same way, y is changing more rapidly with x1 than x2. So x1 is more important, right? And how do you determine the importance? It is determined by the slope of the line. So slope or the coefficient, y is equal to mx plus c plus where m is the coefficient, right? So whether you call it slope, coefficient, weight, importance, they all mean the same in machine learning. So slope or the coefficient of the features are the weights given to the features. So this is a fundamental concept of a sketch in machine learning. A sketch of machine learning data is essentially a set of weights, right? Um, so, so for instance, in this example, once we get this line, we can pretty much throw all this data away and only deal with the line to answer questions about the data. Agree? So yeah, the slope indicates the rate of change of y with respect to the rate of change of x. So greater the slope, more the importance, right? So this line is the sketch of all these 20 or 30 data points, right? You just need to know the slope and the intercept and you're good. You can answer any questions about the data. I mean, to a reasonable scope, um, within a reasonable scope, right? So you can throw away all the data. So that is what machine learning models do. So they throw away the data and then retain the weights. So when you download a large language model from Hugging Face, for instance, it is basically a set of floating point numbers, which are weights or parameters, right? Um, so a model is in machine learning is essentially a series of floating point numbers which represent the weights for the features. That's it. So that's a fundamental concept of a sketch in machine learning models. Uh, what so another what are the latent features of these data points? Any guesses? What are the features that are hidden in these data points? So if you want to throw away all these data points and save just a few values, like in the puzzle we discovered, we talked about, what are the hidden features? The features are basically the slope and the intercept, M and C. In machine learning parlance, they are called weights. The first weight is called W0, which represents the bias in the system, right? Now, can we generate new data belonging to the distribution if we know M and C? Can we generate new points? Obviously, yes, right? That is the crux of generative models. Generative adversarial networks, generative AI, large language models. This is the crux of all of those technologies. So you discover the latent features and you can generate new data from the latent features. So M and C are the parameters or latent features or weights. So what are the latent features of these data points if their relationship is linear? So this is a table of data. These are all the features. The columns are the features, typically, right? In databases, in machine learning, traditional machine learning, the columns are the attributes or features or characteristics. They all mean the same, are random variables. And the rows are the instances, items. So, so the latent features again in these points, each row is a data point, is basically weights. So this data, if the relationship is linear, is same as a straight line in the previous slide. We assumed linearity for logistic regression, right? If you suppose if you apply logistic regression, which is a linear algorithm, we assume linearity and proceed with the finding the weights. So the weights are the slopes across multiple dimensions. So if you have the weights for the features, you can throw away the data, you can generate new data, you can test unseen data, and you can do wonders, as you are seeing with ChatGPT and other large language models. Right? So the latent features of ChatGPT, the data on which ChatGPT is trained, are its weights. It's a model file that you download from the Hugging Face website. So it's like billions of serialized floating point numbers, each representing a weight. Okay, another example. This is the last slide about machine learning. So can you identify this data? So there is one feature and then there is a target variable. So what is this data? Can somebody identify? So if you want to design a sketch for this, what would be the sketch for this data? There are like 30 or 40 rows or maybe 20 rows. I don't remember how many I put. But if you want a compact representation of this table, what do we do? So what is hiding in this table of numbers? It is basically a sine curve. Similar, I mean, not exactly, but approximate. Remember, in big data, we are all talking about approximate solutions. So it's a sine curve, right? So if you apply regression on this data, the regression model captures the hidden features. So it captures these hidden features, which show that this is a sine curve, approximate sine curve. So that is the power of machine learning models. It can reveal hidden patterns in the data. And if you apply neural networks, which act like function approximators, you can actually see that the function is a sine curve, roughly, approximately. Right? Neural network is called a universal function approximator. You can pretty much approximate any function in the world, any behavior. Function is basically a behavior. Any function in this world can be approximated. So that is why artificial intelligence is becoming so powerful. So both forms of the model capture the data. This left side data is captured in both forms. So we are essentially fitting a curve called regression so that we can predict target variable for new features, right? So that is the essence of machine learning, chat GPT, large language model, generative AI, facial recognition, fingerprint recognition, and all that stuff. So model is a compact representation of data, a sketch. Okay, now back to our problem. What is a good sketch for to use for filtering streams? So we want to come up with a sketch to represent the data just enough to answer the filtering question. So, so how do you convert a word, like in the Google example, to a number? So that is, so by the way, a lot of these algorithms, big data algorithms, including machine learning, particularly machine learning, they deal with numbers. They convert big data into numbers. So how do you convert a word into number? I mean, it need not be very accurate. I am okay with any approximate answer, but you have to think. Learning is all about thinking, right? You have to apply algorithm, like I showed in this slide, right? If you don't apply algorithm with the experience at education and enrichment, you cannot form the trillion parameter model. So you have that algorithm is called thinking in human beings. So you have to think. So if you are watching in the future, then please think. Pause the video and think. Um, and suppose you convert the data into numbers. How do you convert that number into a value between 0 and n, a particular range, say 0 to 100? So you use what is called as a modulus operator. And in the first case, maybe I don't know if I gave the answer or not, but in the first case, you can convert text, anything into number, or particularly text into number using ASCII values. That could be the easiest solution. But in machine learning, you use what are called as embeddings and all that stuff. But essentially, there are ways to convert any kind of data into numbers. And then there are ways to convert that number into a hash value, right? A value in the range of certain numbers. So let us look at, yeah, the sketch that we are going to use is a hash table. In Python, it's called a dictionary, right? So that is the sketch we are going to use. And the application that we are going to talk about uh, mostly is spam filtering, right? So Hotmail and Gmail filter spam. Because we don't know the exact algorithm, but you can think of this algorithm as applying to spam filtering. So because hash is one of the primary data structures for all these big data algorithms, let us look at the general ideas. So the idea of hashing is to store only a short signature of the elements, typically a number. I should have animated this, I forgot, but anyway, you get the idea. So for the purposes of the next section, John and Sandra are considered to be same, which is not true, right? So that is why there's a potential for false positive search. So when two data items, so what happens is you have a bunch of keys like the names, which are all letters of alphabet. So you can convert them into numbers using their ASCII values or whatever. So that conversion is a hash function. It's called a hash function. Now it is quite likely that when you apply this hash function, multiple data items can map to the same bucket. These boxes are called buckets, right? When they map to the same bucket, it's called a collision. And like I mentioned initially, the use of hash tables is to search like this. We check if the data is present in the hash table. We search in the hash table. If it is present, then we say that it is safe and then pass it through. But because of these collisions, some searches can result in false positives, right? Suppose only Sandra was stored in this bucket and you were searching for John. The search will result in a false positive because John also maps to the same bucket. right? You get the idea? But John is not in this bucket. But the hash function produces the same key, same value. So, so it's a false positive. So that is a fundamental aspect, concept that you need to understand. Uh, so the more different elements we see in the stream, the more different hash values we see. And these numbers need not make any sense at all. There's no semantic significance to these numbers. Um, and the good thing about hash tables is that it is privacy preserving. So we can pretty much discard these keys. Excuse me. Excuse me. Excuse me. I think something, the window is open, some kind of allergic aroma is going on, I think. Anyway, so uh, so once we have these values, we can discard the keys, right? So that is that preserves the privacy. So once we store a value for Sandra, nobody knows that this value is for Sandra, right? So it is privacy preserving in that sense. We can discard these keys and store just the values. So hash is a very powerful data structure, associative arrays. It's very efficient. It's one of the very good inventions, I would think, in software. Uh, so so once again, the idea is basically you store them in buckets, store the data items in buckets. So uh, so a lot of today's data science is based on this concept of key value pairs. Right? Even ChatGPT, which is based on the transformer architecture, is based on key value pairs. Buckets contain values and there are keys associated with the buckets. Um, so one downside or caveat with hash functions is that if the hash function is used to generate binary sequence, if this hash function, whether it is binary sequence or anything, but typically we generate binary sequences for the algorithm that we are going to cover. So if that hash function is not truly random, then the algorithm's accuracy can degrade. Like for instance, if we choose ASCII values are not random, right? Vowels occur more often than the consonants, right? So it's not entirely random. There is some bias there. Vowels have an extra additional bias, right? So in such cases, the algorithm's accuracy can degrade. Um, and the other thing to note about use of hashes in these algorithms is hashing is often used as one-way transformation. So you can go only from keys to values. You cannot go from values to keys, typically in the big data algorithms, not in the traditional hash algorithms. So hash functions in the big data algorithms are used to simulate randomness, transforming names into binary strings, or for that matter, numbers. In this case, these are strings, but um, so perfect hash functions don't exist, and we have to be realistic. But the ones that we use in these algorithms, particularly those that are used in the industry, are random enough to make the algorithm work reliably, right? So now let us look at the algorithm. So, okay, to provide the intuition, we'll look at a simplified version of the Bloom filter. We'll not look at the algorithm itself right away. We'll look at a simplified version. So the input is, of course, first input is a set of keys to filter. For instance, in this case, it could be the genuine email addresses. And then the next input is, of course, the stream of elements. stream of mails, for instance. So Gmail typically gets trillions of mails in an hour or in a minute or something like that. So that's the stream we are talking about. And n is the size of bit array, right? So this is a bit array. This is a data structure or a sketch that we are going to use, right? So this is of the size n, right? So this is basically Bloom filter, the sketch that we are going to use for filtering at the bottom. So first step is to initialize a bit array B of size n with all bits set to 0. So initially everything is 0. That's the first condition. Then we choose a hash function h such that hx will produce a number between 0 and n. So less than n. It can include 0 but not n. Right? We want to generate that kind of a hash function. Why? Because the indexes range from 0 to n, sorry, n minus 1. We want to map this hash to one of these buckets. So that's why we choose a hash function. So the choice of hash function is a hyperparameter. In big data, machine learning, people need to choose a lot of things. Algorithm does not choose them for you. I mean, there are some ways to simplify things, to simplify the choices, but typically people have to choose. The employees or the engineers have to choose. Um, so a hash function is one such hyperparameter. So the first step is to populate bit array using keys in S. So how do we populate? So we set index is equal to hs. So we apply the for each element in the stream, what we do is we apply the hash function to the element. Like if it is a name or if it is an email address, we apply ASCII values. Now I'm just giving an example. And then we convert it into a number between 0 and 11 by using this hash function, and we set the index to that. Then we set that particular bucket to 1. That's it. And so that is how we populate the data structure, the Bloom filter. Now the second step is filtering. Suppose there is a new data item that came in. How do you know if it is genuine or spam, right? So what we are going to do is for A in stream, for the new elements, we are going to again do the same. We apply the same hash function. The h has to be the same. You cannot apply a new hash function here. It has to be the same hash function with which this was populated. And if the index is already set to 1, then you just say that, yes, this is a genuine email address. If it is not, then say that it is not a genuine email address and filter out the spam. Filter it out as a spam. Right? So that's it. Of course, this is a simplified version, but the real version of Bloom filter is not too complex. If you understood this part, then Bloom filter is very easy. So this is quite straightforward, right? So initial state, all zeros. Then at the time of insertion, we set some of the items are tuples in the stream are x1, x2, and x3. So we compute the hash function for x1, x2, x3, set the corresponding bits to 1. So the corresponding bits to 1. And then, so this is actually the Bloom filter. I think this slide should have gone later. So this is actually Bloom filter. So now can you guess what is the difference between the algorithm we talked and the algorithm on this slide? So in the algorithm we talked, there is only one index to which an element maps. But if you see here, there are multiple indexes to which each element is mapping. So what does that mean? It means that we are going to use multiple hash functions. That is the only difference in Bloom filter. So x1 is a data item in the stream. We apply three hash functions and we set three indices to 1, right? We'll see why. Why can't we just live with one hash function? We'll see why the reason. Similarly, for x2, we apply three hash functions. x3, we apply three hash functions. And we set the corresponding indexes, those buckets to 1, right? And when a new element comes, we search. We again compute the same three hash functions. Um, if all the three buckets have a 1, then we say that yes, this data item is in the uh, safe addresses or known addresses or known items. If it is not, like in this case, there is a 0. One of the hash functions returns an index which has 0 in the bucket. So therefore, x4 is not in the safe list or known list. So we return negative. Now, this part is good. This part is really good. We are able to search using just zeros and ones. But what is bad is that it is capable of returning positive results even when the item does not exist in the safe list. So that is the reason why you see some spam emails coming into your um, inbox, right? Because of the false positives, right? So in this case, x5 maps to the same three indexes, right? Using the three hash functions. All three are set to 1 as x3. So the algorithm falsely returns that x5 is in the safe list and the email goes into your mailbox. So that is the problem, right? The problem of false positives. So what is the trade-off that we are making? Bloom filter trades memory for accuracy, right? Memory and even efficiency. I mean, this is a common theme across all the algorithms that we are going to cover today, right? So that is Bloom filter. Simple idea, right? Uh, so how do you reduce the false positives? So now that we know that there could be false positives, the next goal is to reduce the false positives. How are we going to do it? Any guesses? So the idea is every one in the filter can potentially result in a false positive, right? Uh, Assuming there's only one hash function, say for instance, the the more the number of ones in this array, uh, the more the chances for false positives. So how do you reduce the rate of false positives? We will make the filter long enough to minimize the number of ones. So the Bloom filter is given by this, filled with, initiated with the safe values or known values. So each one is a potential for false positive search. S is a set of keys or the safe values or known values. So typical heuristic is the length of the Bloom filter is 8 times the safe list or the known list. S is a set of keys, right? Right. So it is typically 8 times. So only 20% of the Bloom filter is filled with ones. The remaining, sorry, 80% of the, one second, let me think. So 8 times, right? Yeah, so it is 1/8. Um, so 1/8 is filled with ones. Um, the remaining 7 by 8 is filled with zeros. So majority of the array is zeros. right? So you make the array pretty large. So Bloom filter represents a set, basically, right? If you look at this is basically a set. You can consider this as a set of uh, bits. It represents a set, a probabilistic set where existence is probabilistic and not deterministic. You cannot for sure say that if the element of if the tuple maps to a one, it is safe, right? There's a chance of false positives. Um, so it is not deterministic, it is probabilistic. So there are two kinds of replies, probably yes or a firm no. So some of you must be familiar with this sentence or phrase. Yes means maybe and no means no. It does not exist, right? In this case, it does not exist, but in real life, it means more serious things. No means no, right? So that is the data structure. So if it is yes, if the algorithm returns yes, then it means maybe. If it returns a no, it means absolutely no. The element does not exist at all. And the purpose of the hash function is to generate uniqueness of the items. It doesn't do a great job. Um, in fact, in some of the algorithms, we deliberately make sure that it doesn't do a great job. Like in case of min hashing, which we will not cover in today's class, in today's tutorial. Um, but for these algorithms, the idea is to reduce collisions, but it is not perfect. Uh, the GitHub algorithm that we saw GitHub in the beginning, right? So GitHub generates a unique hash value. It is so unique that collisions occur extremely rarely. The SHA value that you see for every commit in GitHub is a hash value. GitHub applies a hash function to generate that value, and that value is so unique that collisions are rare. But we don't want to use that level of complexity for our algorithm because we want real-time quick answers, even if they are approximate. So bit vector is longer than the number of items in S to minimize false positives, chances of collisions. So we already talked, B is 8 times S. Only 1/8 of the bit vector is filled with ones, typically. And of course, Bloom filters can lie. False positives. A spam email address is output as belonging to S, where S is a list of genuine email IDs. Again, why do false positives happen? Because of collisions in the hash function. Collisions resulting from the hash function. Uh, uh, so, so there is another error called false negative, which happens when a genuine email address is reported as not present in S, right? So that means a genuine email address um, is reported as not present in S. Is this possible? Can a genuine email address be reported by the Bloom filter algorithm as not present in S? The answer is no, right? Why? Okay, let me check if I'm missing anything in the chat window. Oh, I'm sorry. There is something in the chat window. You got muted. Oh, sorry. Okay. So there was a question. I hope the question got answered. Is n the buffer size of the stream? So n is not the buffer size of the stream. Um, you just keep counting, right? So by the way, we don't have to store. So we used n for the proofs, right? We don't have to, in the algorithm itself, we did not keep track of n as such, right? in some cases. But in some cases, like, yeah, you're right. Reservoir filtering, reservoir sampling, we did keep track of n. So yeah, we need to keep track of n sometimes. So as the data comes in, we need to keep track of n because we need the probability to compute the probability with which it is kept. Um, so yeah, we need to keep track of n, and that n keeps incrementing. Okay, sorry, I missed the questions. I should change the. Actually, if I had the Q&A panel open, not the chat panel. But anyway, I'll observe the chat panel also now that I know. Uh, okay, so false negatives are not possible. Why? Because no means no. If the algorithm results says no, then you're guaranteed that it is not a genuine email address. So that is the biggest advantage. So one part of the confusion matrix, there's something called confusion matrix with 4 boxes, 2 good boxes, 2 bad boxes. The 2 bad boxes are false positives and false negatives. So one box will always be zero for us for Bloom filters. So that is a good part. What happened? Okay. So can Bloom filters result in false positives and false negatives? No, only false positives, no false negatives, because no means no. Yes means maybe. There could be it could be a false positive. So the idea is better that there's a famous saying, right? I think this is from Mahatma Gandhi or something. Um, Better that 10 guilty persons escape than one innocent suffer, right? So that is the philosophy of Bloom filters. Now for some math, right? Um, we need to find the error analysis. Like, why do we have to do this? Why do we need to analyze errors? So that we can generate better, we can better the algorithms. So actually, I already covered the Bloom filter algorithm, but the intuition behind Bloom filtering will come out through this math discussion, right? So we need to analyze the problems with using just one single hash, right? So a false positive occurs when uh, an element is not in S, but the bit in the bit vector is set, right? So this happens when HA collides with HS. The hash function returns the same value for A and S for some S in the stream. Uh, So no false negatives, because if it says no, then it is no. So one box in the confusion matrix is zero for us, which is good. We don't have to worry about false negatives. So let n be the size of the bit array, m be the number of keys in S, and h be the uniform hash function over 0 comma n. So the hash function returns a value between 0 and n, like we saw before. The probability that a bit remains zero after hashing all m keys is given by 1 minus 1 by n to the power m. Why? Why is that the case? So what is the probability that a bit is set? What is the probability that a bit is set? There are n number of bits in the bit vector, and one of them is set. So the chance that one of them is set is 1 by n, simply, right? What is the chance that it is not set? It is 1 minus 1 by n, right? So the probability that a bit remains zero after hashing all m keys is that. And the probability that a bit is set to 1 is 1 minus p0. Oh, sorry. So there are, so this needs to, so we forgot one aspect. So if there was just one item which needs to be stored in the bit vector, then it is 1 minus 1 by n. But there are m items to be stored in the bit vector. So therefore, and all these m items are assumed to be independent of each other. Uh, so they're assumed to be independent of each other. So that's the reason why the probabilities of joint events, which are independent of each other, we just multiply them. So we multiply 1 minus 1 by n m number of times, we get 1 minus 1 by n to the power m. So that is the probability that a bit remains zero even after populating the m number of keys in the bit vector. Now the probability that a bit is set to 1 is 1 minus p0, that is 1 minus 1 minus 1 by n to the power m, right? This is quite easy. Okay. Now we are assuming that the hash function is extremely good. So that's called a uniform hashing assumption. Every bit has equal chance of being selected in S. So that is a very idealistic assumption, but we make that assumption to do our analysis. Otherwise, it's going to be extremely complex. So now let us look at the probabilities. The chance that the bit vector, the bit in a bit vector is set to 1 for an element A, and A is not in the safe set that hashes to I is same as a chance that any random bit in B is set. Agree? We are assuming uniformity basically. So the probability of a false positive is equal to the probability that a bit is set to 1, right? I mean that is common sense, right? I even prepared a slide for that, right? Where was that slide? Yeah, this slide, right? So if it is set to 1, there is a chance of false positive. So the probability that of false positive is basically the probability that the bit is set to 1. So that's what we are doing here. And we are assuming there's only one hash function right now, right? Um, so, so the probability of a bit being set to 1, like we saw before, is 1 minus this whole thing. Now we are going to make a small manipulation. Can somebody guess why we are making this manipulation? Any guesses why we are making this manipulation? So the reason we are making that manipulation is because we know that the limit of 1 plus 1 by n to the power n as n tends to infinity is the Euler number E. It's an irrational number. It's a very powerful number used in many contexts. Natural logarithms base is also E. It was invented by Euler, so that's the reason why it is denoted by E after his name, Euler, E-U-L-E-R. So we know this limit as n tends to infinity. So for us, it's a stream, and stream is infinite data. So n does tend to infinity. Um, so, uh, so this whole expression can be written as 1 minus e power minus m by n. This minus is 1 minus is coming because of this 1 minus here. But 1 minus e power 1 minus 1 by n to the power n is e power minus n, and e power minus n can be written as this, right? So you get the idea, right? So we want to simplify the expression to something which is better known to us. E is better known to us. So the false positive rate now is 1 minus e power minus m by n. So now you see the reason why n is 8 times m, right? The greater that ratio, the lower the probability if you use just one hash function. But Bloom filter, we already know uses multiple hash functions. We'll know why. We'll mathematically we'll know why in the next by using this analysis. So if n is equal to 1000, which is the bit array size, and m is equal to 100, number of keys, false positive rate is approximately 0.095. So I deliberately used 10. Uh, the ideal, I typically use number is ratio is 8, but I use 10 just to show the impact. If you increase it to 10, then the false positive rate is 9.5%. I think if you set it to 8, if you set it to 8, I think it is around 12%. But if you set it to 10, it is 9.5%. But remember, we are using only one hash function. Things will change if we use multiple hash functions. Again, we are making an assumption of independence. Stream elements are not correlated with keys in S, right? So otherwise, we will not get these multiplications in the probabilities, right? It will be much more complicated. The model will be much more complicated. So you're understanding how everything is playing up, right? So, so that is the analysis. So the error rate is given by 1 minus e power minus m by n. Now, how do we control this error rate? So if there are more keys, uh, other parameters being constant, if there are more keys, then more bits will be set. Therefore, the false positive rate will increase. We already know that, right, from this slide. Where was this slide? Because of this slide, the more ones that are set in the bit vector, the more the chance for false positives. So greater the false positive rate. Greater the larger the bit vector, more buckets implies less false positive rate. Better hash function, fewer collisions, you lower the false positive rate. So you can do all the three. You can use better hash functions, which will result in fewer collisions. You can increase in bucket size, the bit vector size. You can increase you can reduce the number of keys. So you can, all the three of them can be done depending on the circumstances. But there is another way of controlling the false positive rate in a much better way. See, this more keys is typically not in our control. In hash function, you have to be really a genius to get the ideal hash function. So these are slightly difficult. So why not, what if we add more hash functions is what we want to consider. And that is what brings us to the idea of Bloom filter, which we already talked about. So how can we reduce the number of false positives? So the sketch we will use is called Bloom filter. Why is this not animating? So it has nothing to do with flowers, by the way. The flowers are blooming, I know, but it has nothing to do with the flowers. It is named after a researcher called Burton Howard Bloom. That's why it's called Bloom filter, named after the scientist who invented it. So the false positive rate analysis that we covered is also popular in machine learning, particularly in ensemble methods. We do similar kind of analysis, error analysis. So the idea is that uh, probabilities are less than one, and if we multiply the probabilities, or if we square the probability, um, or we take a power of the probability decreases, right? That's what we do in ensemble methods. How do we reduce the error rate, which is a probability? We multiply with additional probabilities, error rates, by using an ensemble of machine learning methods, algorithms. So similar idea here. Instead of machine learning algorithms, we use hashing algorithms, right? Because the error rate is primarily stemming from the hash function. If we use multiple hash functions, just like we use multiple machine learning algorithms, we reduce the error rate. So we repeat the event. The event in this case is the hash function, hashing. So it's continuing to bloom. Okay. So Bloom filter with multiple hash functions. The algorithm pretty much remains the same other than using the hash functions, and the pseudocode needs to be changed just for the multiple hash functions. So as you can see, um, I highlighted the changes in the algorithm in the pseudocode. So instead of one hash function, we have k number of hash functions. Choose k independent hash functions. The rest of the steps is the same. Again, for computing the hash functions, we do it from in a loop from 1 to k. Again, the remaining steps are the same. And for the search also, there's a loop. We need to loop on all the hash functions. And that's it. That is the algorithm. We just use multiple hash functions. That there's no other change than what we talked earlier. Um, so the good thing is the algorithm uses very little space uh, per element. We are storing in bits for each tuple, not in bytes. And the percentage of false positives is controllable. And this algorithm is heavily used in many applications. Um, so it's a probabilistic data structure. So initially all are set to zeros. Here we are using three hash functions, and we set all the uh, indexes returned by the hash functions to 1. And then in the case of searching, so we again compute the same hash functions. And so in this case, it seems to be a false positive. Is that so? Um, yeah, anyway, you get the idea. So we are computing the hash functions for Donald Knuth and Edgar Dijkstra, who are like well-known figures in computer science. Anyway, we'll take a real example and see. So initial Bloom filter is, we will take the example of spam filtering. So we'll choose k hash functions that map email addresses to positions in the Bloom filter. To make it simple, I did not use any complicated hash functions. So once again, please feel free to post your questions either in the QA panel or in the chat window. I am looking at both, and let me check once to see if there are any. Okay, there are no questions yet. Okay, so we'll use only three hash functions, and I'm not, to make it simple, we'll use ASCII values or email length. So in this case, the first hash function is the length of the email ID, email address, and our bit vector is 20 bits long. So that's why we need a modulus operator to 20. So H2, we are summing up the ASCII values of the character. I mean, these are dumb hash functions. These are not really intelligent, and they are biased. They are not perfect. But for illustration, that's okay, right? So, so this is the second hash function, which is sum of ASCII values. Of course, modulus 20 to make sure that the return value fits into one of these bit vectors. And the third hash function is first character's ASCII value times 2. I mean, I just came up with these randomly because I wanted to make it simple. So insertion, the first email address we got is bob@example.com. So h1 is the length of the string percentage 20, which is 15. H2 is the ASCII value 98. ASCII value of B is small b is 98, O is 111, so on. So you add up all of them, percentage 20 is 14. H3 is similarly the whatever we defined, 16. So we set bits at position 15, 14, and 16 to 1. Now the Bloom filter, 14, 15, and 16 are set to 1. Next comes charlie@example.com. So we again compute the 3 hash functions. Even at the time of insertion, there is a collision. Why? Because the hash functions are very dumb. Um, so this results in a collision. For one hash function, there's a collision, the other two are good. So the new values that we are going to, new indexes that we are going to set are 19 and 18. Similarly, we are going to insert the new email ID, Dave@example. We set the bits. So eventually we have the Bloom filter with how many email IDs? 1, 2, 3, 3 email IDs set to this bit vector. So that is the insertion. So this is the training part. In machine learning parlance, this can be thought of as a training part. We are populating the sketch, just like we are populating the model in training, we are populating the sketch here. The sketch here is Bloom filter. So now there's a new item, email address, that comes in the stream, alice@example.com. We want to know whether this email address is safe or not. So the Bloom filter we have, the sketch we have is this. Now we are going to compute the 3 same hash functions. So bits at position 16, 15, 14 are already set to 1. So that means this email address is good. So is this correct answer or is this a false positive? So in the previous slide, alice@example.com was not there. Bob was there, Charlie was there, Dave was there, B, C, D. Alice was not there. So this is a false positive, right? But the good thing is there will not be any false negatives. If it says it's not present, it means it's not present. So now with Bloom filter, let us do the analysis. How does the error rate change? So now we have k bits for k hash functions. For each element, each tuple, we have k hash functions. So k bits are set. So, so the total number of bits set attempted is k times m. So the probability will change accordingly. So instead of m, we have k times m number of bits, and which is equal to e power minus km by n. So P1 is 1 minus e power km by n. A false positive occurs when all k bits checked for a non-member are set to 1. That means we have to multiply this with k, P1 k times. So that's why we get to the power k, right? So I took an example again, instead of 8, I took 10 to just illustrate. Like before, the false positive rate was 9.5%. But if you use for one single hash function, but if you use 2 hash functions, the false positive rate falls down to 3.3%, which is almost 1/3. So there's an improvement of 66%. improvement just by using additional hash functions. See, that is the ingenuity of these algorithms. These are amazing. So if we, even if we control all these things, we would not have achieved that level of accuracy, that level of efficiency by just adding more hash functions. So that is the ingenuity of Bloom. Um, Burton Howard Bloom, who invented this algorithm. So just by adding one hash function, the false positive rate reduces from 9.5% to 3.3%. So, so does that mean that we keep on adding hash functions to make it zero? That is not the case. Why? Because if you plot the false positive rate to the number of hash functions, the ideal value when the ratio is 10, that means there are 10, the bit vector is 10 times the size of the safe elements, safe emails. Then the false positive rate is lowest when the number of hash functions used is 6.93, which is roughly 7. So 7 hash functions is the best that you can get. After that, the hash function, you use more than 7 hash functions, the error rate keeps going up. So at this value of k, the lowest value of the error is 0.082, which is really good, right? It is how much? It is 0.8%, right? Which is less than 1%, which is really good. So once again, what are M and N here? M is in case of spam filtering, M is the number of safe emails and N is the number of buckets. So we can actually, I mean, I computed this number 6.93 using a program, but you can do it mathematically. How do you do it mathematically? You take the derivative. If you take the derivative of this function, p is equal to 1 minus e power k with respect to k, you get this and equate it to 0. You get the minima for this. So you can do it analytically, but I did it programmatically. Um, so one small thing, small difference, or small manipulation that you can do is, uh, do you want one big bit vector or k small bit vectors? The error rate is pretty much the same either ways. You can compute. I will not go into the details much, but the error rate will be the same. But keeping one big b bit vector is simpler, right? So, I mean, you have to think in multiple ways. So, like Bloom thought about he was not content with this. He thought, how about if we add multiple hash functions? So, similarly, one thought you should get is, what if we split this bit vector into multiple segments? Will it improve or will it worsen? The fact is the error rate will not change, but for simplicity, we are going to keep it as one single array. Okay, there are multiple applications. NoSQL databases use Bloom filters. Cassandra uses Bloom filters. Redis is heavy on Bloom filters. Redshift and so many other databases use Bloom filters. So typically, Bloom filters are used for predicate pruning. There is something called predicate pruning. Uh, so, so processes like predicate pruning can be achieved using Bloom filter. That means you check if certain predicate is met. Uh, so predicate is like a filter. So I'll not go too much into details. And Apache Spark uses Bloom filter. This is the code for Bloom filter in the Apache Spark source code. Um, Actually, I can click, but anyway, you get the idea. So there are several other Bloom filter applications. Microsoft Bing uses for searching. Chrome it used Bloom filter to identify malicious URLs, but it stopped. I mean, from what I heard, it stopped using Chrome Bloom filter. The reason is because because of privacy issues, if I remember correctly. Uh, uh, so so imagine if this was not accomplished by the Google Chrome. If it did not identify malicious URLs, the whole world would be probably impacted, right? You click on a malicious URL, it could go to ransomware. I don't know what all it can do, but it uses Bloom. It was using Bloom filter to identify malicious URLs. Um, And Bitcoin uses Bloom filters to speed up wallet synchronization. Again, privacy became an issue. Actually, one of the advantages I started with was privacy, but there can be issues with privacy also. There can be privacy issues with Bloom filters also. We'll see why. Grafana uses Bloom filter. Um, So there are many, many applications. So if you go to the industry, you are very likely to encounter Bloom filters if you are into data engineering. So why is privacy still a concern with Bloom filters when all the keys are discarded? The reason is the probabilistic nature of Bloom filters means that with enough data, an attacker can still make educated guesses about the underlying data. So that is why websites make sure that we are human. They ask you to solve a puzzle or things like that, right? Because by repeatedly clicking, they can figure out data. So this I covered in a different video. It's available on YouTube as well. The privacy issues, the video on it's on the channel of University of Bolton. Um, so an attacker might try to infer patterns or relationships within the set by repeatedly querying the filter with different elements, just like you guess passwords, right? Just like that, you can keep on uh, giving data and guess, oh, this returned false, this returned positive, this returned negative. So, oh, this may be in the data set and things like that. So suppose if a healthcare provider uses a Bloom filter to store the medical records of patients who have tested positive for lung cancer, an attacker might try to infer the prevalence of the disease with a specific demographic by repeatedly querying the filter with names and other identifying information of individuals from that demographic. So there are ways. So that is the reason why many websites make sure that you are human and you're not overusing the tool. Like Google Scholar, for instance, it has for every query that I make in the last 1 week, it has been asking me to prove that I'm a human. Unfortunately, um, in some cases, it might be possible to reverse engineer the Bloom filter to extract information about the underlying set. So you can reverse engineer the hash, basically, that's what it means, right? So there is a lot more to cover. Let me see. There's a lot more to cover, but I will cover one more algorithm because we have covered only two algorithms. This is an interesting algorithm. So I'll cover one more algorithm. Um, um, so this algorithm is for the cardinality. So what is cardinality? In set theory, cardinality means counting the unique elements in a set, right? Um, so we want to maintain a count of the number of distinct elements seen so far. So there are many applications for this again. So for instance, IP address tracking. So routers often need to estimate the number of distinct IP addresses passing through, and they have limited memory. So routers, right? Routers are hardware, mostly hardware. There's a lot of software also, but it's predominantly firmware sitting on hardware. So it is constrained, memory constrained. So that is one application. The other application is anomaly detection. So if there are sudden spikes in unique connections or requests, so that can signal a denial of service attack, right? DDoS or other network anomalies should also be detected. And another example is tracking how many distinct users visited a site over time. And then product popularity. So counting how many unique users viewed or purchased a product. So there are many. I mean, counting is a very fundamental aspect of processing. And um, unfortunately, because it's a stream, counting becomes difficult also. We need to design algorithms even for counting in with streams. Um, so another application and another interesting application is traffic heat maps, right? If you see Google Maps, it will show some areas in red, some areas in blue, some areas in yellow, and so on and so forth. And also metering lights. How do you when how do you determine when to turn on the metering lights and when not to turn on the metering lights? So we don't know the exact algorithm that Google or the traffic engineering folks use, but this is a good application scenario for counting. So, and counting unique items. For instance, if a car is scanned twice at the same intersection, maybe because of a U-turn, then we want to count it only once, right? We don't want to count it twice. So this behavior reduces noise in traffic data and avoids overcounting. Um, so if you have noticed social media posts, you will notice it counts the number of impressions, right? LinkedIn and Twitter. So left side is LinkedIn and right side is Twitter. Um, you can see the number of impressions being counted, number of users being counted, all these things. And I can for sure tell that these analytics are not accurate because, I mean, I don't want to be very specific, but something happened to a microblogging site. I will not name which microblogging site and what happened, but you can guess. For that microblogging site, after that event happened, my impression count drastically dropped down. And even when there are like 5 or 6 likes, the impression count is like 7 or 8, which is very unlikely. Why will only 5 or 6 people, all the 5 or 6 people in out of 7 like if only 7 have seen, why will all 5 or 6 like the tweet? Very unlikely, right? Um, so, I mean, I gave the answer, I gave my secret away, but anyway. Um, so these counts are definitely approximate. I'm 100% sure, and they are using an algorithm like what we are going to talk now. Uh, and the interesting idea is, can somebody think how we can count the items in a stream quickly? A stream has billions and trillions of events flowing through. How can you count the number of events? Can somebody think? So the interesting idea in this algorithm is using binary representation. So we'll remember I told you that everything needs to be converted to numbers. We deal with numbers when it comes to big data. So everything has to be converted to numbers. So the count anyway is number, and that count will convert it into binary representation. And then we will use the trailing zeros in the binary representation as a proxy for cardinality. So instead of storing every unique impression or member, or in case of traffic, car license plate, the algorithm uses the number of trailing zeros in binary representations of hash values. Isn't that interesting? So hopefully it made you curious. I know it's getting late, but I want to cover this algorithm as well. It's a very interesting algorithm. Um, so using of course, we already talked about the privacy preserving advantage because hashes inherently discards identifiable data. So for instance, once a license plate is read uh, and converted into a hash value, it cannot be retrieved from the hash value, right? That is the advantage of hashing. So that's how it makes becomes privacy preserving. Now the question is, how does the trailing zeros indicate the number, the count of the items is the question. So that is the interesting part. So you have to think about that. How is that possible? So in the future, if you're watching this in the future, just pause the video and think about it. So I'll give a hint. Suppose every second student in the class wears a cap, right? And I saw the first student with a cap. How many students would be in the class so far? I saw a student in the cap, and every second student wears a cap in the class. I saw only one cap so far. How many students are there? Okay, I'll not wait for the answer. The answer is 2, right? Every second student wears a cap. Now, suppose every fourth student has a mustache, and I've seen one student with a mustache. How many students are in the class? Most likely 4, right? So we are going to expand this intuition, right? So this algorithm is very powerful, very widely applied, but it evolved through generations. I mean, generations in the sense like research generations. So the first was initial idea came from Flageolet and Martin in 1985. It was called probabilistic counting algorithms for database applications. Then Durand worked with Flageolet and came up with log-log counting of large cardinalities. So from probabilistic counting, they implemented a log-log efficient complexity counting. Slight modification. Then 2007, Flageolet worked with Gando and others in 2007. And then they came up with this idea of hyper log, right? This evolution is continuing. I think the recent version of this algorithm is called hyper bit. I was recently looking at the website of a researcher, and he had this hyper bit on it. So there are many applications, Hadoop, Apache Kafka, Redis, all of them use counts. So I will not explain how they are using it. Hyperlog log, HLL stands for hyperlog log. And it's used for various counting applications in their tools. So you can read when I upload the slides. But the intuition is, yeah, like I mentioned, if every fourth student in the class wears a cap, and we have seen one student wearing a cap, how many students? 4. What is the probability of finding a student with a cap in the class? 1/4. Implies the probability can be used for counting, since the frequentist probability is always about counts. How do you compute probabilities? By computing the counts, right? So probability is an indication of the count. If a stream of natural numbers has encountered 5 even numbers so far, how many numbers may have been in the stream? Any guesses? So 5 even numbers. So every other number is even, right? So if you have seen 5 even numbers, then in all likelihood, there may have been 10 numbers total, because 50% of the numbers are even. So how do you recognize even numbers when represented in binary? So how do you recognize even numbers when represented in binary? When the binary number ends in a 0, right? So more intuition. Suppose a large stream of real numbers are mapped to their truncated integers represented in binary. So we'll take examples, it will be clearer. So approximately how many of them will be mapped to locations ending in 0, 0, 0, 0, 0, 0? So let us take an example. So 50% are even numbers. So 1, 0. So 50% of the numbers end in 1, 0, definitely. And out of those 50%, um, there are a few of them which end in 2 zeros. Approximately 25% of them, of the natural numbers, end in 2 zeros. So that is 1/4 of the natural numbers end in 2 zeros when we represent them as binary digits. And 12.5% is 1/8 and so on and so forth. So you get the idea, right? So every second number in the stream is expected to map to a hash location ending in 0. Every fourth number in 0, 0, eighth number in 0, 0, 0, so on and so forth. So if we save, so if we have seen a number that maps to a hash function or a hash location ending in 3 zeros, there may have been 2 power 3 or 8 locations in the hash table already filled. You're getting the idea? So that means if we have seen a number that maps to a hash function, hash location ending in R zeros, R is the maximum zeros so far, there may have been 2 power R locations in the hash table already filled. Agree? So that is how we are going to estimate the number of distinct elements based on maximum number of trailing zeros. Now remember, this has to be distinct. It cannot be repetitions. So how are we going to take care of the distinct nature? We'll see that also. So, now by now I hope you develop the intuition that the maximum number of trailing zeros gives you a good estimate of the logarithm of the number of distinct elements. The logarithm is to the base 2, of course. So by finding the maximum number of trailing zeros, you are essentially estimating the rarest event that occurred. Rare events become more likely as the total number of tickets uh, increase, right? Items increase. So we consider all tuples, in the above case real numbers, in the stream mapping to the same location as same. So like in any hash function, right? If the tuple maps to the same bucket, it is treated, two tuples map to the same bucket, they are treated as identical. So the unique number of elements so far we have seen just seen a tuple getting mapped to a location with maximum of r zeros is 2 power r. So now we understand how you handle duplicate items, right? Duplicate items map to the same bucket. So if three items are the same, they map to the same bucket and count as only one item, right? So that way, hashing takes care of duplication and repeats by mapping to unique locations. So that is why the count, uh, the number of trailing zeros in the binary representation gives you an estimate of the distinct elements. Of course, we have to apply a hashing function. So if it is a car license plate, we have to apply a hashing function to convert it into a number between the buckets to fill. So let us look at the pseudocode for the algorithm for counting. Again, we need to select a hash function that will map our stream elements to binary numbers. And this hash function should be good. That means uniform distribution, minimal collisions, and all that good stuff. So the goal is to estimate distinct elements in a stream. So we initialize a hash function. And initially we set the maximum trailing zeros seen so far to 0. So we haven't seen any item yet. So the trailing zeros is 0. I don't know why this is not moving. Okay. Um, then we process each element in the stream, right? So for each element in the stream, we compute the hash function. So we compute the hash of the function. So this r is equal to 0 is a key variable, right? It tracks the maximum number of trailing zeros we have seen in any hash value so far, right? So this is the key for counting the cardinality. So we compute the hash for the element A in the stream, h of A, and then we count the trailing zeros in the hash value. So count trailing zeros of hash of A. And then update. Now we are going to update remember we want to keep track of the maximum number of trailing zeros, right? Why? Because that's what is the indication for the count, right? So each time, so it's like simple sorting algorithm. We always track the maximum number of trailing zeros in R, capital R. So then we estimate the distinct element by using the raising it to the power 2, raising R to the power 2. Sorry, raising 2 to the power R. So the key intuition here is that the distribution of trailing zeros is influenced by the size of the cardinality n, right? You get the idea? So then we return the estimated count. Simple algorithm. So we just keep track of the number of zeros first. Sorry, we just keep track, we count the number of zeros and only keep track of one number, which is the maximum of the number of zeros seen so far in the binary representation of the hash value. That's it. So let us take an example. So these are the car plate numbers, right? So these are the car plate numbers. We have to convert them into hash values. So you apply some hash function, which for the first car plate number, it returns 12. Convert it into binary. Binary is 1100. The trailing zeros is 2. Number of trailing zeros is 2. The second car plate number, hashed to 8. Binary representation is 1 followed by 3 zeros, trailing zeros 3. 5, there are no trailing zeros, right? Because it is ending in a 1. So on and so forth. Okay, so this is computation of the hash values and binary representation and trailing zeros. So we keep track of these numbers in variables. So hash A is 12, RA is 2, R capital R is maximum of 0 comma 2, which is 2. Similarly, for the second car plate number, we do the same thing. Third car plate number is a duplicate. This driver must have taken a U-turn and came back. So it's a duplicate. So the hash value remains the same. And the maximum value does not change. So as you can see, we are just keeping track of one number, which is the maximum number of trailing zeros. So we keep doing this for each car plate number. And so far, we have seen the maximum number of zeros we have seen is 4, trailing zeros, I mean. So the estimate is 2 power 4, which is 16 distinct elements. But we have seen only 1, 2, 3, 4, 5, 6, right? So it is not a great estimate. So it can be off by a lot, right? So we need to improve the algorithm, but the intuition remains the same, but the algorithm needs to be improved, right? Uh, so that was the initial proposal of Flagelle Martin, first version of the algorithm. So, but again, we have to, for every algorithm, we need to prove that the intuition is right? So how do you prove that the intuition is right? So I hope I'm not missing any questions, right? Let me check. Okay, it's been quiet, probably because I did not answer the questions initially. Sorry about that. I missed the QA panel. I was observing the QA panel, not the chat window. Anyway, um, so why does it work? We need to again prove it mathematically. So if you hash n distinct elements uniformly, again, we are assuming that the hash functions are really top notch and they work very uniformly. So half of them will have trailing zeros, right? Because it is generating natural numbers. And half of them will have trailing zeros, and half of them will not have any trailing zeros. The numbers which don't have any trailing zeros are odd numbers. The numbers which have at least one trailing zero are even numbers. So 50%, 50 are even, 50% are odd. And we have to remember that the duplicates in the stream do not affect R, the capital R, because they hash to the same value. So the algorithm automatically handles duplicates without any special logic. Okay, so 1/4 will exactly have one trailing zero. So 1/8 will have two trailing zeros. So you get the idea, right? So actually this should be 1/4 should be 2. So I think I goofed up, I think. So this should 1/4 will have exactly two trailing zeros. 1/8 should be three trailing zeros and so on, right? Um, so the maximum trailing zeros you see is R. It suggests you probably have around 2 power R distinct elements because you need roughly 2 power R elements for there to be a good chance that at least one of them hashes to a value with R trailing zeros. So this is all the intuition that we covered earlier. But then um, we wouldn't have 2 power R plus 1 elements uh, because if we had 2 power R plus 1, I mean anything more than 2 power R, then we would likely have seen r plus 1 trailing zeros. Agree? So it's like um, right. Uh, so so 2 power r therefore is the lower bound of m, the number of distinct elements, right? Once again, why? So if this was not clear, I think I will repeat it here. So probability indicates the rarity of element. If you have seen a number with r trailing zeros, by probability intuition, we have seen at least 2 power r elements. The number with r trailing zeros is that rare. That's what it means, right? See, um, so if there is a number generator, right? Like hash function is a number generator. If it keeps on generating numbers, and if you have seen a number with 10 zeros, then that means it has generated a lot of numbers by then to generate that kind of number, right? That's the idea. If you have seen a number with a max of capital R trailing zeros so far, by the same intuition, the number of distinct elements m should be greater than or equal to 2 power r, right? Otherwise, there's no chance that the same analogy, right? If we see every second person wears a cap, and if you have seen a person with a cap, then there should be at least two people who are in the sample, in the class, right? So the same analogy, I'm expressing it mathematically. Now the interesting part is that 2 power r is also the upper bound. Did I miss anything here? Nothing. So 2 power r was a lower bound. We already, our intuition proved that the 2 power r is lower bound, but 2 power r is also the upper bound of m. Why is that the case? If suppose m was greater than 2 power r plus 1, right? That means 2 power r is not the upper bound of m. Then by the probability intuition, we would have seen a number with r plus 1 zeros, right? The same intuition. But r is the maximum number of trailing zeros we have seen so far. So therefore, m cannot be more than 2 power r. So therefore, the upper bound of m can be approximately considered as 2 power r. So 2 power r is both the upper and lower bound of m. That means 2 power r is a good approximation for m. So that's what we, that's how we prove it. So, so that is the idea. So in practice, um, so there's a practical problem. What is the problem? What if an initial data point randomly, I mean, it could happen, right? In the stream hashes to a number with many zeros, resulting in a count that is way off. Like suppose the second number was uh, 512. I'm just giving an example. Or 1024. Suppose the second number was 1024. 1024 has 10 zeros in the binary representation. But we just saw two numbers, but the second number itself was 10, and the next few numbers are also much less than 100. So the count will be way off, right? 1024, second number resulted in a distinct count which is way off the real count, right? So what is the solution? Any guesses? So like before, we are going to use multiple hash functions, right? We are going to use multiple hash functions. Uh, so, um, so you get the idea, right? We use multiple hash functions. So one of the hash functions is chosen randomly or based on certain criteria. And then uh, the others are also chosen randomly. Now, it is very unlikely that all the hash functions will generate the same hash value, I mean, same value, same number of trailing zeros. Suppose the first hash function resulted in 1024. It is unlikely that the second hash function also results in a number with 10 zeros, 10 trailing zeros, right? It is very unlikely. So that way we avoid, um, of course, we need a way to aggregate these hash functions. How are we going to aggregate? Can we average those hash functions? Probably not, right? Because if one large value, very large value, um, is an outlier, if we average it, it will still pull the average towards the outlier, right? So average is not a good solution. So what is the other way we can combine the hash values? So you're understanding, right? So we are going to create multiple hash functions, and we are going to run the algorithm for multiple hash functions. We compute capital R for multiple hash functions, and then we need to aggregate these values of R. Um, so, so the main problem is the value growth of 2 power R, right? So the probability keeps becoming half when R, capital R increases by 1, but the value keeps doubling. That means the statistical expectation of 2 power R is pretty much infinity. So what is expectation? Expectation is the value multiplied by the probability. The probability is getting lower, but the value is increasing. So when you multiply the probabilities with the values, it becomes, and add them up, it becomes infinity. So the expected count is going to be infinity, which is not a good idea. So infinite count does not help in achieving anything in practice. So the solution is to partition samples into groups, take the median of the median count for each group, then average the medians, right? So the medians are taken to avoid uh, outliers, right? Um, so the whole problem, you're understanding, right? The whole problem is because the algorithm is powerful, but it is also sensitive to outliers because a small change in the number of trailing zeros causes drastic change in the cardinality. So averaging across buckets smooths out anomalies and improves estimation accuracy. That averaging cannot be arithmetic average, mean we take either median, or sometimes some algorithms like I think hyperlog uses harmonic mean. So harmonic mean, we all know, dampens the effect of outliers. So it'll make sure that one hash value with an unusually long run of zeros does not impact the algorithm adversely. And the good thing about using this partitioning samples into groups and using multiple hash functions is that there is a lossless union property. We can merge the results from different groups, from different machines, without losing accuracy, right? So you can, so this is a very powerful feature for distributed systems. You can have multiple machines to process each of these samples or groups, uh, produce independent counts, and they can all be combined because there's no loss in dividing the um, sample into groups. And another technique that is, okay, so let me go ahead. Hyperlog uses harmonic mean, like I mentioned, and we use median to avoid the effect of outliers on average. Average is impacted by outliers, but median is typically not, right? And this is particularly true because of the rapid growth of the estimate. Um, and another technique that is used, it is, I think it is used in the algorithm called super log. So what is done in super log is 30% of the groups with the highest averages are simply dropped to minimize the effect of outliers with large zeros. So the extreme outliers are excluded. The 30% takes care of of the extreme outliers. So only 70% lowest averages are used. So the good thing is the algorithm achieves near constant space complexity. That means order of one, right? The complexity is almost constant space. And the name log comes from the mathematical insight that the number of bits needed to store the maximum number of trailing zeros is approximately double logarithmic. So this double logarithmic behavior is key to the space efficiency. So now we can extend the flagellum art into sliding windows, but I think it's already late. I have 33 more slides. I don't think I'll be able to cover all of them today. So I'll probably save them for some other day. So any questions so far? I know some of you are joining from the East Coast. It must be really late. Uh, any questions? Let me check. Okay, looks like there are no questions. So thanks everyone. Hope you gained. Okay, so there are messages. I learned so much. Thanks. Okay, thank you. Thanks for the feedback. Okay, is there any other? Okay. Okay, so thank you everyone. Thanks for the feedback, and I'll post these slides online in a few days. It won't be immediately, but it will take a few days for me. I need to clean up the slides a little bit, and I'll post the slides. And hopefully you'll join the future events as well. I will end the session now.